Thank you. I would like to thank the organizers for attending the lecture. And for giving me this opportunity to speak here. So I will report on a recent joint work with Wang-Qing Lu from Marseille and with Ahmed Zeriai from Toulouse, who is in the audience. And we are trying to develop the first steps of a parabolic pluripotential theory. So we have posted 2 papers on the archive last October. Both are quite long and a bit technical. They are close to 60 pages each. So I'm not going to explain all of them by far, but I will try to focus on one of them that deals with the compact setting, which is a bit easier to explain. And so what we try to develop is to understand complex Monge-Ampere flows, especially the case of the Kähler-Ricci flow, by means of pluripotential techniques. So we try to define and understand weak notions of solution to these flows. And there are basically 2 natural approaches. So one is by approximation by smooth flows and developing a priori estimates. This is the path I'm going to try to explain today. And another one, which is quite useful as well, but maybe a bit more technical to explain, is by means of a Perron technique of envelope of weak subsolutions. So this one I will skip today, but it's the inspiration nevertheless lies behind what I'm going to explain. So the main motivation is the study of the Kähler-Ricci flow, which you can write like this. And we try to understand this evolution equation, not only so at first on smooth manifolds, but you try to run it for as long as you can, and then try to extend the definition of the flow as soon as you reach finite time singularities. And very soon you need to understand this object on mindely singular varieties. And actually, it's quite common to study the so-called normalized Kähler-Ricci flow, which can be written that way, where lambda is a real parameter whose sign with this way of writing things is the same as the sign, say, of the first class of the canonical bundle of the manifold. So if you pick maybe I should write here that at the level of cohomology classes, so if you write alpha t, which is the cohomology classes of those scalar forms theta t, then alpha t dot solves a very simple ODE, namely that, maybe I should write that way, alpha t dot is given by this. So you, from there and from the initial Kähler class that you give yourself, understand that alpha t has a definite and simple form. So we can pick, maybe I should write it here, a smooth representant of this form in alpha t, so a fixed class. And then solving this nonlinear equation, turns out to be equivalent to solving the following Monge-Ampere, complex Monge-Ampere flows. So n will be the complex dimension of the manifold. where dV is a fixed volume form on the manifold, h is a smooth and fixed function, and phi t is the unknown function which is assumed to satisfy the following positivity property. So it's a well-known fact that, which is particular to Kähler geometry, that solving this Kähler version of the Ricci flow, or the normalized version, is actually equivalent to solving a complex parabolic complex Monge-Ampere equation at the scalar level. So rather than having an unknown tensor, you actually end up with trying to solve an evolution equation for some unknown function, scalar function. So that's the kind of equation I'm going to focus on. But as I mentioned, it's also extremely important to understand this type of equation on mildly singular varieties. So the precise setting will be the following. As Gabor explained, so assume now that the underlying variety is actually mildly singular. It still makes sense of considering such an evolution equation. And in order to understand the corresponding complex Monge-Ampere flow, we fix resolution of singularities and lift the problem to the smooth manifold X, and the corresponding flow transforms into, so let me write this notation for complex Monge-Ampere flow, transforms into the following type of equation. Where so F looks similar to what we had before, so something like some function h of t of x plus lambda phi of t. So this hasn't much changed, but there is a new, or maybe h tilde, there is a new guy here, g, which has the following form. And the zeros, so these are holomorphic sections of some line bundles, and the zeros of those guys actually corresponds to the nature of the singularities you started with. And you obtained both poles and zeros for this density. But the important point from an analytic point of view is that you nevertheless end up with a density G, which is LP integrable. And this is one possible meaning for the fact that the singularities you are dealing with are mild. And then there is an extra difference, is that you have lifted here, omega t is actually the lift of some eta t, So eta was the Kähler form on the manifold V, but so omega t is no longer strictly positive. It has some degeneracies above the singular locus of the manifold you started with. So you have a lack of positivity on the reference form, and you have also some analytic difficulties coming from this density G. So in the sequel, I will focus on this general form of the complex Monge-Ampere flows, and I would like to make sense of weak solution to this flow in the sense of pluripotential theory. So rather than working on the manifold X, the first hint that we follow is that we work on the manifold xt, which is a real manifold of dimension 2n plus 1. So this is the maximal existence time for this flow. And this is a real manifold of dimension 2n plus 1. And we want to understand this equation on xt. So we are going to interpret both sides of the equation as positive measures on xt and trying to make sense of this both left-hand side and right-hand side in the sense of measures. So the left-hand side is the easiest one to deal with. Namely, the only part you need to understand, or the somehow delicate part you need to understand, is this one, which is a complex Monge-Ampere operator. And this has been studied in the late 70s by Bedford and Taylor. And they propose a very convenient definition of the complex Monge-Ampere operator. As soon as, say, for all t, the map x goes to phi t of x is omega t parasymonic and bounded. So I will assume that my object here, I will impose that they are locally bounded. And I want to impose that they have some plurisobonicity property, which means that, so definition, phi t is omega t parasymonic. If and only if you write locally omega t is I dd bar of some guy, say ut, then phi t plus ut is a plurisobharmonic function. So the first condition we impose is that this function phi of t and x is, you can think of it as a bounded family of omega t plurisobharmonic function. And if you do so, then by Bedford-Taylor theory, this is well defined on X for each fixed t as a positive measure, positive random measure, and then you average this with respect to the Lebesgue measure in time, and you have a nice, well-defined measure, positive measure on xt. So that's for the left-hand side. And maybe I should emphasize that we have good, very good convergence properties of this operator. Phi goes to dt wedge omega t plus I dd bar phi t to the n. For example, if I forgot to mention that, of course, in practice, both in theory and in practice, you can almost never compute this object in reality. So what you do is you approximate them by smooth guys, and you want to be able to pass to the limit in the approximation process. So it's crucial in this weak theory that you have reasonably good convergence properties. And here in the Bedford-Taylor setting, there are tons of such continuity properties. And if the phi t's, for instance, converge, if you have approximants that converge uniformly, then you can pass to the limits inside this Monge-Ampere operator. There are many other properties, but let's stick to this one for the time being. So now I would like, and this is perhaps a bit newer, to make sense of the right-hand side. So what do we have on the right-hand side? Well, something reasonably nice, something that is independent of time, and then there is this time derivative that shows up. So something that is quite natural is that if we assume that t goes to phi t of x is, say, locally Lipschitz, uniformly in the space variable, then dt phi is well defined almost everywhere, and therefore you can make sense of the right-hand side in the Lebesgue set. So this is well defined almost everywhere. You plug in the rest of the picture, and you end up with almost everywhere well defined right-hand side, or the density of the right-hand side, hence a well-defined right-hand side. So that's first naive observation that you might hope that you will be able to produce a priori estimate so that your objects are indeed locally Lipschitz in time, and we will do so. But it's also a problem that it's not sufficient to pass to the limit in approximation processes. So we actually add for more. Namely, we wish that our solution have some convexity property in time. So we want that t goes to phi t of x is almost concave. And again, locally, uniformly in 0t times x. So now if you have so forget about the semi-concave problem. Imagine you have a sequence of concave functions. If they converge pointwise, then you can indeed take a time derivative and you have convergence of the time derivative. So the convergence properties are guaranteed if you can make sure that your object have concavity properties in time. One last remark is that we don't, or we shouldn't, ask for Lipschitz property or concavity property all the way down to time 0, because as you may know, for the heat equation, and the same property holds for the Kähler-Ricci flow or complex Monge-Ampere flows, those flows have very strong smoothing properties. So you can start from an initial data that is poorly regular, and the flow will have the tendency to smooth out the initial data. So you can, it's natural to expect that you have good regularity in time for positive time, but you shouldn't expect good time regularity in time up to time 0. So the local here is, you should stop the uniform estimate before time 0. Okay, so that's the definition of the left-hand side, the definition of the right-hand side, and what can we do with this? So the theorem I would like to explain is the following. Assume that capital F is continuous in the three variable. Assume, moreover, that it is quasi increasing in the last variable, which I will denote by R. So this is f of t x r. And locally semi-convex in the last two variables. No, sorry, in T and R. So these are the assumptions on F. Assume G is in LP, like for instance this example, P bigger than 1. And the set where G vanishes has volume 0. And finally, assume that you pick an initial data, which is omega prosumonic with respect to omega 0, and say bounded to start with. Then there exists a unique phi which solves the problem with the appropriate regularity. Namely, so for all t, x goes to phi t of x is omega prosumonic on x. 0 maybe phi is bounded. Let me write it like this maybe. You cannot get bounded up to a time t, but it's bounded up on just a bit, if you start just a bit before t. Okay, so it's locally bounded, but it's essentially bounded. Second property, t goes to phi t of x is locally uniformly semi-concave. Phi solves the complex Monge-Ampere flow equation in the sense I just explained. And finally, phi t goes to phi 0 as t goes to 0, say in L1. So with this type of regularity, and with this definition of weak solution, there exists a unique weak solution in this sense of such complex Monge-Ampere flows.
So capital T is the maximum time where omega t is a Kähler class?
Where actually you give yourself data like this, so it could also be you need for F to be well defined as well. So if your data is well defined on this manifold, then you can solve the problem like this. So of course, you have in mind that for the Kähler-Ricci flow, capital T will have the tendency to be the maximal cohomological existence time. Okay, so I would like to explain the proof of this result. But before that, I would like to stress to mention a few earlier works and stress some differences. Maybe one comment, but maybe more for the experts. The convergence that we've got at time zero is actually quite strong. So I put the weakest one. It is sufficient to get uniqueness of the solution. But as we will see at some point in the proof, the convergence is in a reasonably strong sense. So in capacity, for those who know what it is, are almost by above. Or if you start with some phi 0 which is continuous, the convergence is actually uniform. So there are strong information on what happens at time 0. But for this statement, especially for the uniqueness, which is quite delicate, L1 convergence at time 0 is sufficient. So one comment on previous works. First, that actually motivated this one. So first, there has been an important work by Song and Tian. It has been published only recently, but the paper goes back to 10 years ago. They developed weak solutions in similar contexts, but asking for the manifold V to be algebraic. There is a projectivity assumption in the process that is actually unnecessary. And perhaps more importantly, they prove strong regularity in on the regular part of V. But since this is very demanding, the method is not very flexible. So beside the fact that it's natural to expect that this kind of techniques will be applicable in the Kähler context, more importantly, the techniques that they propose, which are quite interesting, produce stronger results where it can be obtained, but brings techniques that are not very flexible. So it's important to develop softer tools. And this is something we have been doing with Philippe Sidieux some time ago. And with Ahmed Zeriai. And I should also add that part of the work was completed by our PhD student, To. This between the last few years. And in these works, we have developed parabolic viscosity theory. That's a rather different approach, producing weak solutions as well. And here the drawback is that we need to assume maybe with these notations that, there is a G missing, no? Oh, it was here maybe. So we need to assume that the density G that I was mentioning, for the viscosity technology to work, we need data that are continuous. And in particular, the density that causes some trouble has to be continuous, not LP, a bit more demanding than that. And so, for instance, for the application to the Kähler-Ricci flow, or the study of the Kähler-Ricci flow, it implies that the singularities that you can deal with are canonical. And there is an important class of singularities that show up in the minimal model program, the so-called terminal singularities, that are not covered by this approach. While the one that we propose today applies to the most general singularities encountered in the classification of algebraic geometry. Yeah, and finally, a last comment on previous works. So there have been work by many authors. Let me maybe mention a work by Peter Topping in the few years ago, and definitive work by Dinezza and Lu, which essentially shows that you can start from a very arbitrary initial data. So the initial data, which I denoted by phi 0, can be, say, almost arbitrary. In the presentation here, I asked for the initial data to be bounded, but you can extend this hypothesis by far, and this is a work that Eleonora and Chin Lu have done. So this could be also done here, but it brings some extra difficulties that we hide under the carpet. Okay, so the goal now is to give you a few hints on the proof of this result. And the technique, it's not a surprise if you've been following carefully the lectures by Gabor. You approximate by smooth flows, and you try to prove a priori estimates. So that was the main hint in Gabor's first lecture. And this is exactly what I propose to do. So let me write it that way. Assume you have this following equation. But assume just for now that omega t is scalar, a Horner scalar form, that f is a smooth function, and that g is a smooth and positive function. So in practice, it means that you will have indices, approximants, that fj will be a family of smooth functions uniformly convergent towards the f, which is merely continuous, that omega t will be omega tj, omega t plus some extra positivity factor, etc., etc. But the notation will be awful, so I skip that. And I focus on proving a priori estimates for this approximate without too many indices. So the first claim, the claim will be that first, in this context with the initial data phi 0, then phi of tx is uniformly bounded, maybe on 0t minus epsilon cross x. Second, that t times dt of phi will be bounded by yet another constant. And lastly, that the second time derivative is also under control. In the following way, t squared times d double dot t is less or equal than the third constant on 0t minus epsilon dot x. So that's the goal, okay? And once again, you should imagine that there is an extra index j that you are approximating, and of course, in the statement, all the constants that you end up with are actually independent of j. So, how to prove that? So I will try to give some hint. So maybe let's have a look at the first, which is the easiest estimate. And it relies on Yau's solution to the Calabi conjecture, plus some extension due to Guedj and a paper that has already appeared in previous lectures. Namely, you pick a function, or maybe I should write some notation. So you fix some uniform bound. So I haven't been precise on what are the assumptions on the family of forms. So the precise assumption that we actually need will show up for each a priori estimate. So for the first one, we need to have a uniform lower bound, uniform in time. This depends on x. This depends both on time and space variable. This depends on x. So you can bound from above this family of semi-positive form by a fixed scalar form. That's given for free. That's cheap. But more demanding is that you need a positive lower bound that is uniform in time. And by Yau's solution to the Calabi conjecture, you can fix some potential, rho plus or rho minus, Pluripotential with respect to this form, and bounded such that theta plus minus plus I dd bar of rho plus minus to the n solve the equation Monge-Ampere equals GdV. So this you cannot exactly do because of mass constraints, but you can adjust by a fixed constant here, which guarantees that the mass of the left-hand side and the mass of the right-hand side are the same. And once you do that, there is a unique such solution up to normalization. So for the plus, this is really Yau's solution. For the minus, because here the form has the tendency to degenerate, it's not really Kähler. This is essentially the work that was mentioned by Guedj and EGZ. So once you do that, then you observe, for instance, that u plus of t and x, which is rho plus of x plus c t plus 1, is such that is actually greater or equal than phi t of x. So that's the claim. And let me say one word to how to justify this. What you can observe is that due to this inequality, phi t is a subsolution to the flow, to the following flow, theta plus ddc v to the n dt is e to the dtv plus f t x v gdv. So actually, the point is that theta plus ddc phi t to the n, because theta plus is a bit more positive than omega t, this is greater or equal than omega t plus, oh sorry, I tried to avoid ddc since the beginning, but they caught me up. So you have this inequality. This is the equation satisfied by phi t. And now, okay, so that's the first observation. Phi t is a subsolution for this Monge-Ampere flow. And now you compare to the fact that U plus, the claim is that U plus is a super solution to this flow. If C is large enough. So I leave that as a computation. And then you apply the so-called comparison principle. Once again, we are working with smooth approximants, so it's a classical maximum principle that you plug in here, which tells you that, as the name suggests, the subsolution is smaller or equal than the super solution. Okay, so I'm running out of time. So I will skip the Lipschitz estimate, which is a bit tricky, but I would rather say one word about the last one, which is probably the newest of the three estimates. And maybe let me give a proof of this when under simplifying assumption, namely, I will assume that f is 0. This simplifies a bit, but it's still a bit technical, so I will assume, moreover, that omega t is given like this, so it's affine. And in this case, the claim can be made, the estimate is even better, namely that t times the second derivative of phi is less than n. So it's a very precise estimate on the second time derivative. Why that? So set h of tx, sorry? No, so that in this case, if under this simplifying assumption, you can get rid of the square. So consider t times, let me use dot notation to simplify my life. Consider this, and t0, x0, where h reaches its maximum. Either t0 is 0, and then you're done, or let me assume, maybe here, that t0 is positive. Then I claim that if you apply the following heat type operator to the function h, so st is omega t plus I dd bar of phi t, then this is less or equal than phi t double dot minus t divided by n phi t double dot square. So that's the important and slightly tricky computation, but let's assume that for a while, and then look at what happened at this time t0 positive and x0. Then at that point, this operator applied to IH should be non-negative, which tells you that if you multiply by t0 this quantity, T0 phi t double dot minus T0 phi t double dot square divided by n is less or equal than, sorry, is positive. Therefore, this quantity, il y a un truc là qui va pas. No, that's okay. What is missing? No, this is non-negative. I multiply by T0, which is positive, and I end up with that. Okay. And this you can send this guy on the other side, divide by T0 phi t double dot, and you end up with what you wanted. No. But it's n or no? Yeah. Okay. So I was planning to give you the full tricky computation, but poor you, I'm running out of time, so you will miss that. That was the funniest part of the story. Okay. How much time do I have, Daniele? 5 minutes? Yeah. So I will skip that because I need more than 5 minutes. So where are we? Here are the estimates. So let's pretend we have a full detailed proof of this. And now remember that we are actually arguing by approximation. And we have this kind of information. So for each j, phi j is a solution of an approximating flow, and we have this kind of estimate on phi j. Then first observation, families of quasi-parabolic functions, if you understand well the negative part of the curvature, are weakly compact in the L1 topology. So this first bond tells you that you can extract convergent subsequence, say in L1 sense, in a poor sense. Then, as I said, if you go now down to the third one, well, the second and the third one tells you that those families of approximants are locally Lipschitz in time, and furthermore are essentially concave in time. So you can pass to the limit in this weak sense, but also pass to the limit in the time derivative, thanks to the concavity. So where is my flow? It has disappeared from the board. Well, where did you say? It is hiding, no? No. Okay, so let me just rewrite that. Oh, thanks. Here it is. So what I just said is that here, on this right-hand side, we can pass to the limit thanks to this information. And I cheated a bit at the beginning, saying that we have tons of continuity results for the Monge-Ampere operator. There is one that we haven't got, is that it's not continuous along L1 convergence. So we need some extra information on how, if we extract here in the L1 sense, how this converges toward the limit. But if you plug in, if you look at the equation that these approximants are solving, what you get here is the Monge-Ampere of the approximants are given by a density times Lebesgue, and the densities are essentially uniformly bounded from above, thanks to the Lipschitz estimate. And in that setting, we have strong stability results for solutions of a Monge-Ampere equation, and we can prove that actually it's not L1, but they actually converge in the L infinity sense. So the approximants uniformly converge towards the limit. And therefore, we can pass to the limit and produce a solution. And with some extra minutes that I haven't got, you can apply this, for instance, to the long-term behavior of the Kähler-Ricci flow on singular Calabi-Yau varieties and get in a few lines that the flow deforms any initial data towards a singular Calabi-Yau metric that Gabor is trying to understand better for us. Thank you.